Well, it at least is very clear that we feel the urgency and that we also feel the knot tied around our necks and that we need to make pace on this. And I think our next speaker, Amory LOVINS, will tell us a bit more about what extra gains might be reached by taking a different view, in which I will explain a little bit more later. Amory LOVINS is the co-founder and chief scientist of the Rocky Mountains Institute. He has served as an energy consultant to major corporations and governments in more than 65 countries, including the USA. He is the author of 31 books and over 650 articles. His major recent contributions include working with China's National Development and Reform Commission on an ambitious efficiency and renewable energy trajectory, working with the Indian government on shared, connected and electric mobility, and exploring integrative design as a norm. He was awarded the Alternative Nobel Prize in 1983. Welcome, Amory. He is going to tell us more about the approach we could take using multiple benefits in the design of buildings, vehicles, equipment, and industrial processes, because they can bring us much more. And he will tell us more about that, about integrative design. Thank you, Amory. Have a nice applause for Amory.
Thank you. Today I would like to remind you about how to design whole systems for radical energy efficiency or other resource efficiency, thus protecting climate not at a cost but at a profit. This practice applies orthodox engineering principles, but it asks different design questions in a different order to get different answers. I teach this material at Stanford, and I plan to post my lectures free online. Around 1975, US government and industry all said that the primary energy needed to make $1 of GDP could never drop. A year later, I heretically suggested that it could drop 72% in the next 50 years. So far, it's dropped 61% in 46 years, with 28 times the cumulative effect of all the renewable growth in the same period. Yet just the efficiency innovations already added by 2010 can save another threefold, twice what I originally thought, at a third the real cost. And today, even that looks conservative, because optimizing buildings, vehicles, equipment, and factories as whole systems, not as piles of little isolated parts, can often make very big energy savings cost less than small or no savings, turning diminishing returns into increasing returns. Economic geologists know that the economically extractable reserves of a mineral are only a small part of the whole resource base, but can expand with innovation or with price. Similarly, reserves of conventional energy efficiency, like the bright green zone in these mineral resource definitions, are several-fold smaller than the full efficiency resource exploitable by integrative design. This paper explains why making energy savings several-fold bigger can actually cost less. Because it doesn't add things, it designs them out. It doesn't use more, but rather fewer devices, and not fancier but simpler devices, more artfully chosen, combined, timed, and sequenced. We're used to resources like copper ore bodies and oil reservoirs, finite and depletable assemblages of atoms. But energy efficiency resources are infinitely expandable assemblages of ideas, depleting only stupidity, a very abundant resource, maybe an increasing resource. So how do we do this magic? Well, one of my early mentors, the inventor Edwin Land, said, don't undertake a project unless it is manifestly important and nearly impossible. He also said, people who seem to have had a new idea have often just stopped having an old idea. That's the hard part. Asian tradition similarly urges us to seek original mind, beginner's mind, child mind, opening ourselves to new ideas by shedding all assumptions and preconceptions. That's the first and hardest step in the method of integrative design. So in that spirit, Caltech's late great aerodynamicist, Paul McCready, reminded us that decades of textbooks on creative thinking have posed this familiar problem as find the solution that will connect these 9 dots with just 4 lines without lifting your pen from the paper. And you can try various ways to do this. 1, 2, 3, 4, oops, 5, that doesn't work. 1, 2, that isn't going to work. And you're supposed to learn to think outside the box, which is where that expression comes from. But one day a student startled her professor by saying she just solved this problem with only 3 lines. How do you do that? 4 was hard enough. Dots are infinitely small. Well, actually these are rather fat dots, and it looks like you don't have to go right through the center of them. So if your paper is wide enough, you could do this. And seeing that, the students started to feel rather liberated. You know what happens then? They started to solve this problem in 1 line. I'll give you a few of the nicer 1-line solutions. You can find some more. If you're Japanese, you might think of the origami solution. If you're a geographer, you might want to use a very long line. If you're a mechanical engineer, a tool-using creature, you could get out a tool called scissors. There was no rule against cutting out the dots. If you're a statistician, you might imagine if you crumple up the paper and keep stabbing it over and over with the pencil, eventually you will go through all 9 dots at the same moment. And the one I like best came from a 9-year-old girl who said, "You didn't say it had to be a thin line, so I used a really thick line." So, as McCready said, this tyranny of the word "the," find the solution with 4 lines, puts us back in the box and keeps us from being more creative and finding more elegantly frugal solutions. So, with beginner's mind, never having built a house before, so I didn't know what was impossible, and that made it possible. In 1982, I did the conceptual and energy design of the owner-builder house where my wife Judy and I live near Aspen, Colorado, 2,200 meters above sea level. Outdoor temperatures there used to dip as low as minus 44 Celsius. We've had 39 days of continuous midwinter cloud. But our house does no combustion. That's so 20th century. Super insulation, ventilation, heat recovery, and super windows that insulate like 16 or even 22 sheets of glass, but look like 2 and cost less than 3, make this house 99% passive solar heated, 1% active solar. Effectively, it's 6,000-year-old North Chinese passive solar architecture with updated technologies. Now, the efficiency added less construction cost than we subtracted by eliminating the heating system, and saving also 99% of the electricity and 99% of the water heating energy and half the water. All the savings paid back in 10 months with 1983 technologies. Today's are much better and cheaper. The house wraps around an 85 square meter central atrium, seen here in a February snowstorm, and it has so far produced 80 passive solar banana crops. Someone said I had really big earphones. But without needing to look like this, and the bananas are optional, our house has helped inspire several 100,000 European passive buildings starting in Germany. And an analogous approach turned out to work fine in Bangkok. Almost everyone on Earth lives in a climate somewhere between Bangkok and Old Snowmass, Colorado. Integrative design gives many benefits from each expenditure. So the white arch at the top of the upper middle photograph, holding up the middle of the building, has 12 different functions, but it has only one cost. So we start with the end-use effect we want. To deliver it, we optimize buildings as whole systems, not as a bunch of components. We pay for the efficiency by shrinking the needed supply and equipment. We maximize those capital savings by applying efficiency from downstream to upstream, as I will explain shortly. We reward the design professionals for what they save, not for what they spend, and we optimize the sequence and timing of design steps. Let me illustrate this sequence idea. with two examples. First, most lighting retrofitters start by installing higher efficacy sources, more lux per watt, and better controls. But the Handbook of Fundamentals of the Illuminating Engineering Society rightly tells us first to improve the visual quality of the task, then the geometry and cavity reflectance of the space, how well it bounces the light around, then the lighting quality, cutting veiling reflections and discomfort glare. That can be good for a factor 7 or so savings. Then we optimize the amount of light, the illuminance. Then we harvest and distribute natural light. And only then do we optimize the luminaires and the controls and maintenance and training. This sequence can often save an order of magnitude more energy, looking better, seeing better, and yet the fixture count and the capital cost go down. However, most practitioners do these steps in reverse order, worst buys first, so they don't save on capital and it doesn't look as good. Or if you want to keep people comfortable in hot, humid places, well, I once asked my hostess in Japan, who lived in essentially a paper house in Tokyo, why don't you heat your house? And she looked rather puzzled and very sensibly replied, why should I? Is the house cold? In other words, we should cool the people, or heat them, not the building, which has no nervous system and no comfort sensation. We should do task comfort like we do task lighting. So in RMI's Basalt, Colorado office are these hyper chairs which keep you comfortable in air temperatures from under 18 to about 30 Celsius, using in the summer 3.6 watts of silent fans, and in the winter 14 watts of automotive seat heaters, all run on a little lithium battery. Then we expand the range of conditions in which people feel comfortable. For example, good ceiling fans expand the summer comfort range by 5 to 7 Celsius degrees. Then we minimize unwanted gains of heat or humidity into the space. Then we apply passive cooling, many techniques proven for thousands of years. Then we use active but non-refrigerative cooling that can give over 100 units of cooling per unit of electricity. Next would come super efficient refrigerative cooling, like Lee and Glock's tripled efficiency but cheaper mechanical systems in Singapore. Next, if needed, would come cool storage and controls. But actually, we don't ever need to get as far down the list as refrigerative cooling, or probably even active non-refrigerative cooling, to save 90 to 100% of the cooling energy with better comfort, better uptime, and lower whole system capital cost, even in the most severe climates. Most practitioners, again, pursue these options in reverse order, worst buys first. And these methods keep improving. So our integrative design to retrofit the Empire State Building saved 38, later 43% of its energy with a 3-year payback. 3 years later, our cost-effective Denver retrofit saved 70%, making this difficult half-century-old government building more efficient than what was then the best new U.S. office, which in turn is only a third as efficient as RMI's passive net positive no mechanicals office near our house. And then there's this Bavarian building using 2/5 less energy than ours. And yet these technologies all existed more than a decade ago. What has mainly improved is not so much technology as design, the way we put the technologies together. And as another example, the Empire State Building retrofit here yielded 6 times the savings that a major energy service company had offered with the same 3-year payback, but using disintegrated designs. So that's one data point on how much integrative design can do that you cannot do without it, factor 6 in that case. Now, Europe needs to make efficient something like 15,000 dwelling units per day for the next 30 years. And it's encouraging that industrializing mass retrofits of houses or bigger buildings to net zero and streamlining their finance and soft costs is now getting cheap enough to finance entirely from saved energy while extending building life for decades and improving amenity, health, and value. So the Dutch Energy Sprong, or Energy Leapfrog retrofit package, adds an industrially pre-built, customized tea cozy around your house. It has even been demonstrated to be installable in a single day while you're at work. And this could be an important element, for example, in Ukraine's reconstruction of undamaged or lightly damaged buildings, and then structural insulated panels with spray-on air tightening and passive designs could quickly replace many of the rest. Another big building example, in 6 muggy Indian cities, 1.5 million square meters of integratively designed offices are using about 80% less energy than the Indian norm, but cost 10 or 20% less than normal to build. And they give superior comfort and satisfaction. So glare-free lighting, as you see in the big floor plate on the right, is delivered throughout by contract. If workers complain of glare and demand blinds, then the architect doesn't get paid. IPCC reported across a range of European climates and building types these decade-old data showing that for quite diverse situations, the best new buildings on the left and retrofits on the right are saving up to at least 90% of their energy without higher cost per unit of saved energy. In both graphs, bigger savings are towards the right and lower cost is towards the bottom. The vertical cost scatter simply shows the business opportunity to conform inferior projects to the low-cost, high-savings projects' best practices, because whatever exists is possible. Now, timing matters too. When you're retrofitting a big glass office tower like the one in the back near Chicago, both hot and cold, super windows plus efficient lights and equipment and deep daylighting can shrink mechanical loads and systems by 4-fold, and that more than pays up front for the efficiencies that shrank them. So a 4-fold efficiency gain in this old Chicago building could thus pay back in about -5 months. In other words, it's cheaper than the regular renovation you must do routinely every 20 years because the glazing seals fail and you need to reskin the curtain wall facade. It's going to take decades to retrofit all of our big buildings, so let's right-time them to make the savings much bigger and cheaper, perhaps using portfolio software at retrofitdepot.org. Tripled efficiency mechanicals in big buildings is well proven, but it may just have become obsolete. In a remarkable recent experiment in Singapore, a shaded 10 square meter pavilion like a bus stop shelter open at the ends kept Singaporeans comfortable outdoors without drying, cooling, or moving the hot, still humid air. People were instead cooled purely radiatively by absorbing far infrared radiation from their bodies into vertical panels on at least one side of them, circulating, say, 17 Celsius water and separated from the humid air by a plastic sheet to prevent condensation. That modest degree of cooling is really much smaller than we're used to. Panels can be cooled to, say, 23 to 25 degrees, and yet can deliver comfort in outdoor temperatures up to 32 degrees at least, with 80% relative humidity. And such little cooling, just say 7 to 9 Celsius degrees subambient, can even be achieved by special surfaces that passively radiate infrared to the sky, even in cloudy or rainy weather, so that in direct sun they feel cool to the touch. And if you combine these two passive technologies, one for radiant heat rejection, another for radiant cool delivery, and perhaps a heat pipe between, you may provide tropical climate comfort in vehicles and in new and old buildings using no or almost no electricity. That would change a lot. Now, inside the buildings, this fist-sized Swiss heat pump can deliver 6 to 15 units of hot water per unit of electricity, and this dramatically more efficient, safe, and otherwise superior Swiss cooking system, including vacuum-insulated pots, can use 2.5 to 4 odd times less electricity than induction cooking. So these kinds of technologies make it much easier to switch from gas to electricity. In industry, which uses half the world's energy and electricity, roughly, RMI's latest $60-odd billion worth of industrial designs typically found 30 to 60% energy savings, paying back in a few years, far better than the brown retrofit zone at the upper left corner, where most energy service companies deliver disintegrated design. In our new build projects, 40 to 90% savings generally had lower than normal capital cost. And these superior results come from rethinking industrial processes and from redesigning basic but often neglected elements like pump and fan and motor systems. For example, in both buildings and industry, better pipe and duct design can save about 80 to 90% of the friction, 97% in my house. And if everyone did this, it could save roughly a fifth of the world's electricity, or half the coal-fired electricity, typically paying back in less than a year in retrofit and instantly in new builds. Such radical savings require two changes in the design process. First, we specify big pipes and small pumps rather than small pipes and big pumps. You see, the friction in a pipe falls as nearly the fifth power of its diameter. So how fat should the pipe be to optimize the friction? Well, the textbooks say to make the pipe just as fat as will repay its extra cost over the years from the same pumping energy. Which sounds plausible, but it's wrong, because it leaves out the capital cost of the heating equipment. The pump, motor, inverters, and electricals must all be big enough to overcome the friction, so their size and roughly their capital cost will fall as nearly the fifth power of pipe diameter, but the capital cost of the fatter pipe rises as only about the second power of its diameter. So when we optimize the pipe as a component, we're pessimizing the system. When we optimize the whole system at once, then we get fat pipes and tiny little pumps, so the total capital cost goes down. Okay so far? This is not very complicated, that's why it's hard. And the second shift in design is even simpler and thus more difficult. We lay out the pipes first, then the equipment. Normally the boilers and tanks and so on go in some arbitrary, convenient, traditional place, and then you call the pipe fitters to come in and please connect point A and to point B. But by then A and B are rather far apart, other stuff got in between, they're at the wrong height, they face in the wrong direction, and by the time the pipe makes its way across the space all dressed at neat right angles like they teach us in trade school, the friction is about 3 to 6 times what it would have been with a straight shot. Now the pipe fitters like this. You pay them by the hour, they mark up the extra pipes and fittings. They're not paying for your bigger pumping equipment up front, they're not paying for your bigger electric bill forever after, but for you as the owner, it would be smarter to make your pipes fat, short, and straight rather than skinny, long, and crooked. Thus, low-friction pipes make the blue pump on the right so tiny that it looks like a decimal point error, and you notice it's raised up to meet the pipe rather than dipping the pipe down conventionally to the pump on the floor and then back up again with 4 right-angle bends. The tan chillers here, normally in a neat row, have been staggered to eliminate the pipe elbows. And yet such rearrangement of designers' metal furniture remains largely unnoticed and unpracticed. It isn't yet in any standard engineering textbook or industry forecast or government study or climate model. Why not? Because it's not a technology, it's a design method. And few people yet think of design as a way to scale rapid change. It may seem incredible that we can save about tenfold in the energy in pumping, the biggest use of motors. And yet your heart at this moment is pumping blood about 10 times as efficiently as industrial pumping systems do. Your body has on the order of 100,000 kilometers of fractal blood vessels down to the tiniest ones. And if those had the design and friction of standard industrial piping, you would need a heart bigger than your body. Very inconvenient. But in fact, your third of a kilogram, 1.5 watt heart suffices because your blood follows nature's standard design, which is called laminar vortex flow. That's a whole other conversation about the other big design revolution, biomimicry or innovation inspired by nature. Back to the pipes, this design logic is unfamiliar because it's so simple. In practically every building and factory, a critical pump with an in-place spare pump is normally laid out like this. So the flow always goes through 2 right-angle bends, friction. Why not lay it out like this so the main flow has no bends and also fewer valves? The same logic applies in the very common arrangement of multiple pumps in tandem. Now, in this California museum, our colleague Peter Rumsey retrofitted and efficient piping layout, you notice the wide joint, the sweet bend, sending the pipe up diagonally 3 dimensions through the air, and of course fat pipes. And this cut the pumping energy by 3/4 with a 2 or 3 month payback. It also eliminated 15 pumps that will never again waste energy and maintenance costs. Then he repiped the other pumping loop and added variable frequency drives, and that doubled the flow and saved 85% of the energy. Peter simply asked the pipe fitters to lay out the supply pipes as if they were drains, because in another part of their brain, the pipe fitters know that if they have a drain driven only by gravity and it has a right angle bend, it will clog. Here's how most big buildings pipe cooling tower water back to the condenser. But if we lay it out instead the way Peter does, everything gets better. The only obstacle is force of habit. We should bend minds, not pipes. What does such savings mean for the pumps and fans that use half the torque of the motors that use over half the world's electricity? Well, from the fuel burnt in the thermal power plant at the upper left to the end use, the flow out the pipe in the lower right, many successive losses compound. So only 1/10 of the energy in the fuel comes out the pipe as flow. But now turn those compounding losses around backwards from right to left, and they become compounding savings. Every unit of flow or friction you save in the pipe saves 10 units of fuel, cost, emissions, and global weirding at the power station. And as you go back upstream, the components get smaller and cheaper, so the total capital cost goes down. So a basic principle is always to start your savings downstream. Start at the end. Start with purpose, with intent. Then your design logic flows back upstream in the opposite direction to the energy flow. Again, I haven't found an engineering textbook that says this. I think they assume the successive steps multiply. Multiplication is transitive, so the order doesn't matter, but as you see, it matters very much. Well, next, your motor systems are now 80 or 90% smaller. That allows a whole drive system retrofit that can save about twice as much electricity as, say, the International Energy Agency found, at about 1/5 the real cost, because it combines not 2 improvements, but 35, 28 of which are free byproducts of the first 7. And if you add that drive system saving to the fluid handling savings, then the combined potential is to save not 1/5, but more like 1/3 of the world's electricity. And then if you added the drive power savings on the non-fluid handling half of the drive power, then it gets to about 1/2. That's a pretty big term not to be in our studies and models. Now let's apply this logic to a very different situation, a big old data center, but you'll see it's the same logic. 2/3 of the fuel fed into the power plant is lost in the plant and the grid. Half the metered electricity is then lost in the cooling system and the uninterruptible power supplies, which together are half the total capital cost. And that's before they reach the servers. Then half the server energy doesn't reach the chips because it's lost first in inefficient, usually very underloaded power supplies, and in lots of fans to take heat that largely shouldn't be there off the motherboard into the room where we can do dumb things with it. The next problem is severe underutilization of computing resources, partly through insufficient virtualization. Well, the resulting energy flows, that tiny little yellow stalk at the bottom, is about to vanish, so let's magnify it. Next comes bloatware, running many unnecessary threads and processes and making simple tasks very complex because compute cycles were cheaper than programmers' attention and someone else was paying for the energy. Downstream of all that, you may even have inefficient business processes. So in all, looking at the red numbers along the bottom, only a few 100,000ths of the original fuel energy is actually delivering customer value. Where should we start to fix this? Downstream. First, write elegantly terse code, optimally compiled, with the goal that every compute cycle is a needed and wanted one. I'd assume this would save an order of magnitude on compute cycles. It actually turns out to be more like 2 orders of magnitude. And now that we're shifting to mobile devices, it becomes very valuable because efficient code stretches battery life. Then even, 13 years ago, we could quadruple server efficiency, now even more. And the servers will need a lot less cooling and power supply, both of which can be done in much smarter ways. And then we could even save half the utility losses by using fuel cell trigeneration at lower capital cost. Well, multiply these savings from downstream to upstream, and you get at least 2 orders of magnitude energy savings, maybe 3. In the actual project for which we made this diagram in 2009, the client rejected most of our recommendations, so we were only able to triple the efficiency at the same capital cost, which was a big disappointment. But our partner EDS said that had our recommendations they agreed with, which was nearly all of them, been adopted, we would have saved about 95% of the total energy use and half the capital cost. We can also save industrial energy by saving the energy-intensive materials that industry makes. 2 papers released last year showed how smarter structural design can profitably save at least half the world's cement and steel that now emit 15% of global CO2. Here are some examples of better structural design. Substituting compression for tension structures typically looks better, costs less, and uses about 1/8 the tons. Pouring concrete into curvy fabric forms, not rigid prismatic forms, can often save over half the concrete by putting strength and stiffness only where they're needed. And then the weight savings compound because you need less strength to hold up less weight. An airy 3D printed bridge can carry mainly its users, while massive concrete bridges support mainly their own weight. Here's a stainless steel bridge that was 3D printed. And most common floor slabs, we just walk on them, we don't think about them, but they're about half the total weight of a typical mid or high-rise building. A typical 8-odd meter span floor slab will be about 30 centimeters thick of reinforced concrete. But instead, you could replace it with a 5 centimeter thick folded concrete floor slab like corrugated cardboard or a shallow vaulted dome. And that costs less and saves 3/4 of the cement and all of the steel. Now, thin floor slabs and better energy design can save a further 15% of core structural materials and 3/4 of the energy in a new mid or high-rise building while increasing net rentable space by a stunning 55%. How do you do that? Well, it's called 3 for 2. You design out a vertical meter of mechanical plenum in the left image at each story, and then you can fit 3 stories with the normal 2.8 meter ceiling height into the current height of 2 stories. Cost, complexity, and time all fall dramatically. Why would you do it any other way? Vehicles can use the same design logic. Automobile's propulsion system or powertrain loses about 4/5 of the fuel energy before it reaches the wheels. But our savings should start at the wheels, and here's why. Just 1/5 of a modern car's fuel energy reaches the wheels and moves the car, and of that tractive load, nearly half heats the air that the car pushes aside, most of the rest heats the tires and the road, and only the last 6% of the fuel energy accelerates the car and then heats the brakes when you stop. But it gets worse. 19/20 of the mass you're accelerating is the heavy steel car. So just 1/20 of that 6%, or about 0.3% of the fuel energy, ultimately moves the driver. Not very gratifying after 1 1/3 centuries of devoted engineering effort. Notice that both the acceleration and the rolling resistance depend on mass, which thus causes most of the tractive load. Now, reducing losses in the powertrain, where most automakers focus, is harder than reducing tractive load because so much more has been done already. And it's also less rewarding because when you save 1 unit of fuel in the powertrain, or energy in the powertrain, you save 1 unit of fuel in the tank. But saving 1 unit of energy at the wheels avoids 3 or 4 more units you don't need to waste getting it to the wheels, and thus leverages 4 or 5 units of fuel savings at the tank. Thus, we should first reduce the tractive load, then improve the powertrain, which gets smaller for the same acceleration, that saves more weight, and it also saves capital cost to help pay for the lightweighting. So it's the same story we already heard in the building and industrial sectors. And I began to think that safe ultralighting of cars might get affordable when I met Dave Taggart, a young engineer at the Lockheed Martin Skunk Works, where he had led the design of a 95% carbon fiber advanced tactical airframe that was 1/3 lighter but 2/3 cheaper than the 72% metal predecessor. And that was too radical. So Dave quit, and 22 years ago I hired him to lead the virtual design with 2 Tier 1 auto engineering firms of something I'd invented 9 years earlier called a hypercar, in this case an ultralight carbon fiber electrified midsize SUV, 4 to 6 times more efficient with a payback under 2 years at US fuel prices. In 2007, Toyota used our shared design methods to create the 70% lighter 1X carbon fiber plug-in hybrid. 6 years later, this profitable quadrupled efficiency carbon fiber electric car came to market. More on that in a moment. Even aluminium fleet vans like this plug-in hybrid we road tested in 2009 could save 1/5 of US light-duty vehicle fuel profitably with no subsidy. And carbon fiber autos could save more oil than Saudi Arabia lifts, but with radically simplified manufacturing. They can be made at normal cost, and we know that because BMW did it in 2013. This carbon fiber electric car that I drive was profitable from the first unit sold 9 years ago, because its carbon fiber was paid for by needing fewer batteries to propel the lighter weight car, and fewer batteries recharge faster with less electricity and less infrastructure. The saved weight snowballs spectacularly. The assembly saves 2/3 of the normal capital and water and half the normal energy, space, and time, eliminates the 2 hardest steps in automaking, and it's much better for the workers. So the quadrupled efficiency comes without compromise and with many driver advantages. Thoroughly applying this design logic could save up to about 2/3 of the scarce battery minerals, and then 5 other multiplicative forms of efficiency could make the rest quite manageable. BMW finished producing this model in June, having profitably sold 250,000 of them, until Tesla was the most popular EV in Europe. But Bloomberg New Energy Finance reports that China's strategy for its 2030 flagship cars includes switching to carbon fiber structures and displacing 4/5 of the steel. I don't think the steel industry has noticed that yet. Now, I'll just zip very quickly through a little eye chart. If you look at the extra retail price of a more efficient car on the vertical axis and its fuel efficiency on the horizontal axis, I apologize for the barbaric units, and for some reason we have lost the feed here. Oh, well, whatever. I don't need that. There are all these official studies. Here are US ones for cars and light trucks at 2 different periods, plus some independent studies, and showing steeply rising cost as you get more efficient. And those are evaluated technology by technology. But then there are 15 empirical data points that have embarrassed those studies within weeks or months of their publication. And basically, these data points show that integrative design extends the design space by a factor roughly 3 towards the right. That is to say, the conventional technology by technology evaluation method that's behind all our efficiency standards misses 2/3 of the design space and makes efficiency look smaller and cheaper than it is if you design it by the car, not by the part. And the game is about to change again, be heralded by 2 hypercars that should enter the market around the end of this year, both from little firms, I advise. Most drivers will not need to recharge this composite 2-seat 3-wheeler or this Dutch 5-seat 4-wheeler, because the solar cells on top recharge them enough for ordinary daily driving without ever plugging them in. So I have a BMW and a Tesla. They're both among the most efficient electric cars on the market. These are 3 times more efficient than that, and they can be further improved. And likewise, in heavy vehicles, Tesla's battery electric heavy truck is being customer tested. Mass production was postponed from last year to next year, so battery and car production can catch up, but it could grow very quickly. And this model more than triples efficiency with 40% sleeker aerodynamics, lightweighting partway that offsets the battery weight, and a 2-year US payback at pre-war diesel prices. And then in the air, there's this flight-tested air taxi I recently inspected They could fly nonstop from Paris to Aspen with 1/6 the operating cost and 1/8 the fuel of a conventional business jet. It's also a good candidate for electrification. They've designed a bigger version, ideal for emerging point-to-point route architectures, and this looks set to blow up aviation's business models. And now there are even higher efficiencies emerging from polymer lattice and membrane structures that can make metal wings and other aerostructures 98% lighter and yet cheaper, tougher, and like a bird's wing, aerodynamically self-optimizing in real time. In 2011, my colleague Lina Bonnet led a synthesis called Reinventing Fire, showing how by 2050 in the United States, at historically reasonable speed, very profitably tripled or quadrupled efficiency in buildings and doubled in industry, could shrink electricity use by a quarter, despite all electric autos and a 2.6-fold bigger GDP. And this quadrupled electric efficiency would cost only 1/10 as much per saved kilowatt hour as we now pay to buy a kilowatt hour. So we didn't buy nearly enough efficiency. By the way, this graph conservatively does not include most of the integrative design opportunity. Over a longer period, perhaps to about the 2060s, the examples I've offered you at about 780 slides of other examples suggest that the global integrative design potential is probably on the order of a 5-fold or 80% saving, and yet this is not normally recognized or taught or delivered or expected or rewarded. Observing buildings and vehicles and factories in over 70 countries in 50 years, I see the same design errors repeated everywhere because they're widespread in our textbooks and our classrooms. So I'm hatching a little plot for, to put it a mite impolitely, the nonviolent overthrow of bad engineering. You know, teaching disintegrated design as we do condemns our descendants to perpetual retrofit of bad stuff. It's not a worthy legacy. They'll have a lot of other things to worry about. So to help us be good ancestors, I'm seeking fellow students and teachers and practitioners to help to collaborate on making integrative design shift rapidly from rare to common. I'd like to help retread the in-practice design professionals and the tradespeople like pipe fitters, sheet metal workers, mechanical contractors, who in fact design many of these systems. I want to help improve design software to allow and coach integrative design and to find iconic chief executives to apply what we might call 5 ADA in their firms and spread the word to their peers, as Jack Welch did with Six Sigma. I'm eager to test the 20 or so known scaling vectors, see what works, and start scaling. Hope to set up a little skunk works at Stanford to do that work. And our partners in India, Australia, and Sweden want to collaborate on pedagogic reform. So I hope these little illustrative examples will encourage you to rethink why global energy and use efficiency is only about 1/9 what it could be. How better design and beginner's mind can help to close that gap, and how we can scale up to make integrative design as common as grass. And then the global energy transformation can move at the pace and cost of design and software, not of infrastructure, and can be not constrained by the inertia of incumbents, but sped by the ambition of insurgents, like I suspect some of you. So go forth and be fruitful and subtract. And thank you all for your good work and your kind and prolonged attention.
Thank you for this very nice presentation with all those illuminating examples of what we can do. And I think you've given us a roadmap for our own house and even for our cars, if necessary, and it is necessary. I would like to invite you to take a seat so we can ask you some questions and go in debate with you and have a discussion. And I would like to ask Valerie and Leah to ask the first questions, and then I will ask you to join us. Thank you.
Yeah, thank you, Amory. I think, I mean, it's great to see all these examples, and I have actually 2 questions. Indeed, yeah, I love that these types of examples. Indeed, I've got actually maybe two questions. One is about actually your last slide, well, integrative design. Do you think it can be massified, or do you think it has to be targeting specific situations? In other terms, do you think to reach carbon neutrality for the USA, France, whatever, for the world, do you think we can go quickly by using integrative design or design thinking?
Well, it probably doesn't apply quite everywhere, but I very rarely encounter a situation where it isn't a good fit. And I think it could potentially spread very rapidly because you don't need to go back to school and learn a bunch of theory to practice it. You remember some of my pipe photographs. I think if a plumber or pipe fitter saw those images in social media, he'd probably say, yeah, I could do that. And, you know, once she understands the logic and sees how the numbers work out, she'll see she could really get a lot of attention in a crowded marketplace by offering that superior performance. So we have here, I think, something that potentially could spread with and at the speed of social media. And we haven't had anything quite that fast before. This is sort of like a social movement, potentially. And I'm actually writing for the chief engineers of China's 17,000 biggest factories, a little monograph with a lot of those pictures and others called Guangdao Jidao, which is the Tao of pipes. Because if only a small number of them get hooked and start applying it in their own factories, word will spread very quickly. So it's, I'm looking at a kind of viral contagion model of spread rather than conventional policy-driven hardware deployment. We're spreading ideas here, not devices.
May I ask another question? Yes. Some of your examples were about retrofit, building retrofit versus new construction, and the efficiency that was targeted in both. Would you say that it's better to go to retrofit, for instance, if we also consider the question of resources? Cement,
that's
steel,
certainly another consideration, and I'm encouraged that the German government has pretty consistently found that deep retrofit doesn't cost more per unit of saved energy and may cost less than shallow retrofit. But also, I mean, just thinking about building insulation, there's extraordinary skill in Germany in very high craft, labor-intensive interior super insulation. You kind of rebuild the building from the inside. On the other hand, the Dutch integrative super outsulation that I showed applies in many situations, especially our terrible social housing buildings. And that permits mass retrofit on an industrialized scale and pace without needing that very slow and difficult to develop level of craft labor skill and without a lot of the costs. So I think we'll end up seeing both, you know, and we'll use the meticulous German techniques on historically listed buildings, for example, where we need to preserve the exterior for architectural reasons. But the Energiesprong looks quite exciting, and I believe in Germany there was just an example where they retrofitted one big facade in 20 minutes that way, just to show how quick the technique can be.
Yeah, you have another question? No? Yeah, go ahead.
I was just wondering how how the rebound effect fits into your studies. I think it's, first of all, thank you. It was very remarkable. I'm really impressed by what can be done still. Yet, for example, in Germany, for the last decades, like the emissions in the transportation sector did not go down at all, even though we had quite, and I'm sure they were not like as extensive as they could have been, but we had efficiency gains for the engines, for example. But they were just balanced out by the fact that we had bigger cars, more cars, and so on. So I was wondering what you think should be done in order to avoid this happening in the future as well.
The rebound concept comes up every 10 years as some economist rediscovers it. This is the fourth time for me. And it doesn't make much more sense than it did the first time. It's a real effect, but it's generally very small, typically in the low single digits of percent. We did count it in Reinventing Fire and our other analyses to the extent justified by sound literature, but that's really quite small. And there are some obvious reasons for this. Typically, the customer does not have an itemized bill showing what got cheaper. They don't have that information. Typically, there are saturations operating. You don't rewash your clothes that are already clean just because the electricity for your washing machine got cheaper. You don't turn down the thermostat on the refrigerator because the milk would freeze, and so on. Transport is a bit different, and there the limiting factor is that people have a time budget and they typically don't want to sit in their car more than an hour a day, even if the fuel gets cheaper. So it may be a bigger car, but that doesn't mean it has to be an inefficient car, especially if we do what the U.S. has done, and I think Europe and Japan need to do, and that is to enforce the efficiency rules by size, not by weight. Otherwise, the automakers get pulled in opposite directions, because in the U.S. we now do it by size. And having helped make that happen, I think there are really strong reasons for it if you want to save lives, oil, climate, and money all at the same time. Industry is much more complicated, very difficult to analyze, but the models that were put about some years ago by Breakthrough Institute purporting to show large and even over unity rebound were simply junk science. They had a severely misstructured model and misspecified data set. So I'm not saying rebound isn't real, and there are actually about 5 layers of it. The only part that's significant is that energy efficiency is a significant macroeconomic stimulus. So if you think economic growth is a bad thing, you might not want energy efficiency because it stimulates more economic growth. And there's some of that strain in the argument for rebound and against efficiency. But I think I guess one other comment, when we go back to John Jevons' paradox, you have to remember that there are certain fundamental technologies like steam engines or electric motors or the internet that so reshape the whole economy that they could be a major economic stimulus. Now, whether that produces more welfare and more justice is another question altogether than the size of GDP. But it's curious how many critics of energy efficiency, in effect, blame anything they don't like about economic growth on energy efficiency. Why not blame emancipation of women or public health or education? You know, these are, again, equally large changes we made in society that changed everything and gave us, in many respects, more prosperity and a better world. What we make of it is, again, a separate question.
Thank you for those remarks. And now I have room for 3 questions maximum. 2, sorry, 2. So I see a question there.
Thank you, Amory, for a very interesting and stimulating presentation. I suppose I've been around not as long as you, I think, because I remember reading your work early on in my career. But I seem to, and I'm not an engineer, so I can't assess anything really that you've said, but every so often there are these sort of transformational things that come up, and if only we did something differently, all the problems would be solved. And it feels a bit like that to me, and I wonder what it takes to go from these fantastic thinking about how to, this idea about how to reorder our thinking to actually making it happen. And yeah, I'd like your thoughts on that.
I think we're at an early stage of understanding all of the obstacles to making integrative design the new normal. But since it's not built into our forecasts or analyses, I think that one of the biggest obstacles will simply be getting particularly theoretical economists to believe that there could be that much white space. There could be a way to roughly triple the size of the energy efficiency resource whilst making it cheaper and often with increasing returns. People with design mind and design training can grasp this pretty readily from the kinds of examples I've given. But I think people who drive by looking in the rearview mirror at econometrics might find it very surprising. And the broader context also is that the kinds of incremental technology-based efficiency improvements we have been pursuing historically for decades with much success face about 60 or 80 market failures, each of which can be turned into a business opportunity. And I think policy would be a lot more effective if it paid more attention to that systematic barrier busting. But these are complex systems, like with 24 parties in the commercial real estate value chain, almost perfectly rewarded for inefficiency, penalized for efficiency, and hardly talking to each other using different metrics and so on. And if you leave one out, it can be a showstopper. So tackling that degree of institutional complexity and perverse incentive does require relentless patience and meticulous attention to detail. I would like to think that integrative design may be easier to do because the leverage of changing design at the front end is so enormous, but it doesn't exempt you from those kinds of obstacles popping up later.
Is there another question in the room? Yes, DJ?
It's just a comment from the presentation on the scenario for France. So we have 4 scenarios, one on sufficiency, one on efficiency, and one, let's say, on technology and so on. So Valérie, after this presentation on radical efficiency technologies, I think they are not taking into account in our scenario. We were, let's say, optimistic in efficiency and so on, but not at that level. Does it change your mind in the occurrence of the 4th scenario after that presentation?
I don't know if it changes my mind, but I think it reinforces my opinion that we both need really a lot of effort in terms of design and energy efficiency solutions, but plus also some more, sometimes it's also low tech or some sufficiency energy sufficiency solutions. So no, I think it doesn't change my mind. It's more we need both. We need both.
Another way to think about this might be that by adding another layer of opportunity. I've made those kinds of very valuable analyses look terribly reasonable.
Okay, I would grant you the possibility to ask questions to Valerie and Leah during lunch, and invite you for lunch. And so thank you all for being here, taking part in this conference. I hope you enjoyed all of the presentations, the keynote speakers, also the side events, and speaking to each other. And we hope, of course, to see you next time. Till next time.